Thank you all for being here for yet another informatics seminar on a Friday afternoon. To reward you, once again, downstairs will be yet another informatics social hour with some food and drinks afterwards. You're welcome to come downstairs and join us there. It's my pleasure to introduce Leo Murta. I've known Leo since 2003, when I've told the story earlier during this visit. When I went to a conference in Amsterdam and had an undergraduate present the work, and afterwards the undergrad was being harassed by two people who kept asking questions. Now usually when one of my students gives the talk, I sit in the back of the room, because otherwise they see my eyebrow raise or my neck twitch when they say something, so I just sit in the back of the room and let them do the talk. So they harassed the student for a little while, then after about 10 minutes said, maybe I need to go rescue the student. So I went up, and then they said, oh, but you're here too. And then I was the subject of the subsequent interrogation for quite a while. So this was Leo, who at the time was a graduate student, and his advisor, Claudia Werner, who worked both at the time in Rio de Janeiro, Federal University of something Rio. And they said, oh, why don't you come by when you're in the neighborhood? And I went, Irvine, Rio's not exactly in the neighborhood. And I said the same thing. I said, why don't you stop by when you're in the neighborhood? About a month later, the phone rang, and Leo's advisor, Claudia, called and said, I'm in Vegas. I'm driving down tomorrow. You said if I'm in the neighborhood, I can stop by, so I'm going to stop by. And I went, whoa, doesn't usually happen like this, but okay. So she stopped by, and we talked a lot. My group did demos. Turned out our research was much aligned, and she said, why don't you come to Brazil? I said, okay, maybe I can do that. And to sweeten the deal, she said, we'll pay your way to come to Brazil. I said, okay, sign me up. And about 3 months before, she says, and you're taking 2 graduate students with you. And I went, hey, wait a minute. I'm paying my own way to Brazil to paying 2 graduate students to go to Brazil. This doesn't sound right. This got more expensive. But I did. And I was really glad I did, because what ended up happening was I had almost like a mini retreat with the 2 graduate students, in the sense that we talked an enormous amount about the work. They had a lot of interactions with the fabulous work that was going on there. And that became, for a little while at least, that became an ongoing collaboration, out of which Leo spent 4 months here as a visiting graduate student, and we did a bunch of work at that time. And now he's an assistant professor still, right? But soon, hopefully, associate professor. At a university very close to Rio. He'll tell you where that is. And I'm just glad he's back visiting us and telling us what he's been up to. So that's an unusually long introduction, and it speaks to the high regard that I hold him in. So thank you very much for being here.
Thanks, Andrea, for the introduction and for inviting me to be here. As Andrea said, I will start talking about the place that I came from. So, and in the morning, we talk about with some people, and we noticed that Brazil, I think almost everybody knows that Brazil is more or less here. But the funny thing is that we are here, and Rio is here. So we are more or less 12 hours flying from Rio. And the time shift is of 6 hours. So it's near, but it's not that near. Brazil is the biggest country in the South America. And if we look closer in Brazil, we can see the Rio de Janeiro state here, and the city of Rio de Janeiro here. The city that we live and work is nearby Rio. It's across a bridge. Its name is Niterói. And here is a picture of the university campus that we work. It's in the shore. And here are 2 new buildings. We hope they will be ready on the beginning of 2014. This picture is quite old, but we are much better. Our computing institute has around 65 faculty, 100 PhD students, and 150 master students. And we have around 3,000 undergrad students. Our main undergrad course is this one, is computer science, but we also have the information system and distance education course in the department. I put here 3 motivations for you to come and visit us in Rio. The first one is academic. we have a program in Brazil named Science Without Borders. It finances students from Brazil to go abroad, and it also finances faculty to go visit Brazil. There are different programs in this way. And we have two other motivations that have nothing to do with science. One of them is the Soccer World Cup next year, and the other one is the Olympics on 2016. If you go to Rio to soccer or Olympics, let me know, and please visit our university. You are more than welcome there. So what I'm going to talk today is about versioning. And it's funny because if you talk with software engineering people about versioning, they probably say that it's a solved problem. It's around for 40 years or so, 50 years, and we have lots of good solutions for software versioning. The problem is that depending on the type of the artifacts that you want to version, the existing solved and good solutions do not work. So I will do a brief introduction about versioning, and after that I will start to detail in 3 different examples about artifacts that do not have a great support for versioning in the software engineering life cycle. One of them is UML models, and then I'll talk a bit about image and video, and finish with runtime components. And at the end, I'll discuss some future work and ongoing work. So Conrad has a taxonomy of version, and he divides version in 3 types of version. One of them is revision, the other one is variant, and there's a third one, actually is a temporary type, which is draft version or cooperation version. So revisions, I put some example here, and the revision example that I chose is the iMac generations over time. Revisions are versions that supersede other versions. So if I have a new iMac, I would probably stop to sell the old one and start to market and sell the new one. So the new version supersedes the other one. Here I have examples of variants. Variants are versions that live together. So they seem like options. They do not supersede each other, but you can select a variant depending on the need that you have. And the draft version or cooperation version are versions that exist for a temporary time in the developer machine. So someone gets the source code or the software artifacts from the repository and start to change the artifact. During the time of changing, you have versions in the workspace that may become a revision or may become a variant, depending on the intentions that you have when you put the artifact back in the repository. So if you want to keep it as a revision, you probably put it back in a separate branch in the repository. But if you want to keep as a variant, you put in a separate branch in the repository. But if you want to keep as a revision, you need to go through a merge operation that combines the different draft versions that exist during the same period of time. So here in this example, the first one that merged is John. He has no effort because he basically is the first one, and there is no change. After that, Mary tries to merge, and I need a way to combine what John did and Mary did. And at the end, I have the Peter trying to merge, and I'm combining the contribution of Peter with the contributions of other developers that shared first. The problem is that after lots of people share their work, I have some chance of not being able to combine the contributions easily. So in this case, John did something that's similar to Fred. And when Fred tries to socialize his change, he's not allowed to because there are some conflicts. and he needs to fix these conflicts through a merge process. In this case, what we usually have in configuration management is the base version, the version that they check out, the version that's currently in the repository, and the version that I'm trying to socialize. So I will get these three versions. I run a three-way algorithm to combine them, and then put a new version back in the repository. Besides this merge operation, we already have other two very important operations in version control. One of them is the diff. These operations receive two versions and try to identify what is the difference between these two versions. Let's assume that these two versions are variants. In this case, the green color means everything that belongs to the right version. And the red color means everything that belongs to the left version. But if we know that these versions are revisions, the red color means deletions, and the green color means additions. So I can interpret what I'm seeing here in different ways if I know which kind of version that I'm operating over. And I have another operation that's complementary to diff, which is patch. Patch receives one of the versions and receives the delta, and it's able to reconstruct the other version, applying the delta over the base version. But why those operations are important? For three main reasons. One of them has to do with storage. If I can run deltas and identify deltas among two versions, I can consume much less space to store the difference than storing all versions as a complete element. The other reason is transferring. When I check out for the first time, I need to get all the artifacts that exist in the repository. But after I change something and I want to put my contributions back to the repository, I do not need to send everything back. I can run a diff in my machine and send only the deltas back to the repository. If I want to update my repository, I can do the same at the server side and send only deltas back to my computer. And the third reason is to comprehend the evolution. If I look to this delta, I can rapidly note what is the difference between these two versions. So sometimes I want to understand what happened among versions, and I can look to the deltas and fast go to the difference that exists. However, I'm talking a separate way of revisions and variants, but if we go to the wide and look real software, we can see that they coexist. I have lots of revisions and variants, commit after commit in the software. Here, I got a small piece of the Git history. This is the history of the Git source code. And we can see that there are lots of branches in parallel going on, and we have lots of revisions. All the time that I have a small ball in the same branch, it means that's a revision over the previous version. And here I have variants in a very strict time frame. But okay, I know what is revision, what is variant, what is draft version, but is this really useful? I think it is very useful, because with this kind of support, I can synchronize teamwork, I can reproduce previous version, I can segregate developers, I can explore possibilities. So lots of things that we do on a daily basis when we are developing software are enabled due to version control. And we have here something that's interesting. Understand evolution. We have a whole area of software engineering which is aiming to mine software repositories that is kind of enabled by the existence of repositories with versions of the software. And actually, we already have lots of systems that help us to version control software. Here I put three of them, Subversion, Git, and Mercurial. but there are many, many others in the open source and proprietary world, commercial world. The problem is that these systems in general, they adopt a very simple and generic data model. They store data assuming that all data is a directory or a file. And if it's a file, it's assumed that it's a binary file or a text file. And text file is decomposed with lines. That's the data model that they use to store the software evolution. This is good because this allows us to use these systems in every kind of software development project. So if I'm going to code an operation system, that's okay. If I'm going to develop a case tool, that's okay. So it's generic. But on the other hand, we have a development process that creates many different types of artifacts. I put here conception with documents, models, architecture, development with code, lots of XML descriptors, images, videos, scripts, and if we think about production, when the software is running, we have components, we have data that's being transferred from different modules and components at runtime. How do we fit all these artifacts in this generic model? Actually, we can do it, but we mostly use this kind of file, the binary file. So if we want to put our fancy UML model in Git, what we'll probably do is save it as an XML file and commit to Git. It's one file with everything that we did in our model. We can think of this UML file as a text file, and it's not a good choice because it has a complex schema that controls how the XML file is written. So if I use a conventional text-based merge algorithm, it will probably not work. And if we put this file as a binary file, we have no control of how the file, the model itself is evolving inside the file. So what I'm going to do from now is to get three types of artifacts to discuss with you why Git, Subversion, Mercurial, or any other usual version control system do not help us to deal with this kind of files. One of them is UML, the second one is image and video files, and the third one is runtime components. So talking about the UML artifact, this is the oldest work that I did regarding this kind of artifacts. I did this during my PhD. The problem that we have is that UML is serialized in an XML file, which is an XML file with a specific schema. And if we look at the way current version control system look at these files, we notice that they consider the file as a whole as a unit of version. What do I call unit of version? Is the element that I can query in the version control system. So if I get a UML file and put in the version control system, I can ask for the system to tell me who are the people that changed the file, when the file was changed, and so on. So it's a unit. And the version control system uses lines as unit of comparison. I mean, they compare lines, and lines has no meaning when we are talking about XML. So we have a mismatch between the data model that the version control system uses and the data model that we need for UML. What did we do to deal with this problem? We conceived a version model that worked direct in the UML meta model. So we do not version files and directory anymore. We version model elements and every type of model element that we may have in the UML meta model. We developed a core-based reflective algorithm for merge. So we are actually independent of UML. We can version any kind of meta model that belongs to a core. And we allow the user to define what he considers as an atomic type. I mean, if he wants to consider classes as atomic type or use cases or any entity that exists in the UML, we will detect conflict at that level. So one key algorithm that we use to propagate changes is to analyze 3 types of changes that we may have in the core level, in the meta-meta level. One of the changes is when an attribute of an artifact changes. For example, if I change the name of a use case or the name of a class, I'm changing the class itself. It's funny because people that are not used to UML meta model think that the name of the class is the class. It's not. They are different elements, but they are related as an attribute. Here I have non-containment relationships. For example, I have a use case and I have an actor, and they are associated. This is a non-containment relationship, and when I have this kind of relationship, I do not propagate the change. So if I change class B and it's related to class A keeps in the same version, and class B has a new version. And we also have containment relationship in UML. For example, a class contains methods and attributes. So if I change a method, I'm changing indirectly the class itself, and I'm changing the package that holds the class, and so on. So here, if I change method X to a new version, I'm indirectly changing the class that holds the method, and after changing the class, I'm indirectly changing the package that holds the class. And I brought an example that helps us to see how this kind of evolution of model works. Here in this example, John has changed the attribute email of class guest to address, but in parallel, Mary added two methods in the guest class, getMail and setMail. So in this screenshot, we can see in the left-hand side the repository configuration. So I just committed the first version of the project. It's one XML file, but internally we can version each model element that belongs to the XML file. This version, the first version, was checked out by John, and he changed the email attributes to address. After changing, he commits back his version to the repository, and we have a second version of the model, which we can see that there is a second version of address that was propagated to the class due to the containment relationship, and then propagated to the package, and finally propagated to the model. However, in parallel, Mary is working over the version 1, which is here, and she added 2 methods in the guest class. So what happens when she decides to socialize her changes? I'm basically running a 3-way diff and merge algorithm, and I'm detecting that these changes are non-conflicting because they belong to the same class, but class is not an atomic type. And we would get something like this, which is odd because she wrote these methods to operate over an attribute that do not exist anymore. But if here is the version 3, combining both versions. So we have now the 2 methods and the address together. But if I decide to say to the tool that I want to class be considered as an atomic type, and I do this with this description, this descriptor file, the tool could detect that 2 people are changing the same class at the same time, and would avoid this changing, showing to the user that he or she should update his version, merge manually in his machine, and then put the version back to the repository. because two people change the same thing at the same time. The second type of artifacts that I want to talk about is image and video. That again, if I put this in Git, they will become a binary file. And Git will store as a whole all versions of the images and all versions of the video. But why images and videos are important? Because depending on the domain that we work, we have lots of them. And they are much bigger than source code. So I got here movie industry, advertising industry, and gaming industry. They use a lot images and video. And before starting this work, we had an opportunity to talk with people that were developing a game for kids with Down syndrome. And we look at the repository and try to understand the artifacts that they use in the game. In their case, they had 81 source code files, 1 video, and almost 200 image files. And the funny thing is that if we go to the size, the 81 becomes almost 0, because code is very small. And if we look at the image, it's almost all the space that's being consumed in the project. And worse, the images change over time because they are designing the game, they are trying different prototypes and so on. So what we want to do with images and videos, we want to be able to ask people to look at two revisions of an image and identify what changed in these two revisions. We want people to be able to store image in the hard drive, not occupying too much space. And we want people to be able to change the same image at the same time and then combine the changes that they did. So why is it a problem? It's because here I have 100 pixel, a 1,000 pixel by 1,000 pixel image. It gives me a total of 1 million pixel. But each pixel has at least 3 channels, red, green, and blue, and sometimes an alpha channel. So I need to perform something around 3 million comparisons to say if these pixels, these images have a difference and generate a delta from this difference. So what we did to deal with this problem is to create infrastructure that provides us with diff, patch, and merge operations over images. And we run this in GPU to accelerate the process. So we can do it fast, online, in a way that we can use in version control. And the delta that we produce with diff has 3 properties that we want. First one, it should be bidirectional. So we want to be able to apply the delta over any one of the images and reconstruct the other one. The second property, we want the deltas to be proportional. The size of the delta is proportional to the size of the change. So if the images change just a little, I want to have a small delta. If the images change a lot, that's okay to have a big delta. And the third property, we want deltas that are understandable. So I want to show the delta to the user, and I want him to look at it and understand what happened with the image. To do that, we use the XOR operation over each pixel in parallel using a GPU. And with the XOR operation, if the pixel do not change, we get black, which is compressible after applying zlib over the resulting image. And if the pixel change, we get the notion of the change. So here I can fastly note that the change belongs to this place, this part of the image. The other thing that is interesting is that the same operation applies to patch, because as I use XOR, I can patch the delta over any of the 2 images and generate the other one, also in GPU. And to do merge using image, what we do is to use a technique named diff and apply. We actually diff assuming here A as a base version and B and C two draft versions that are developing in parallel, I can diff from one side here, generate the delta, and apply this delta over the other side. So I can reconstruct the changes over the other change. In this example, in the left-hand side, I have a base image. Someone put a dish here, and another guy put a sun here. When I run the diff from these two images, I got only the dish, and I can patch the dish over the other image and get the merge result. We also detect conflicts. When we are patched, if we detect that we changed the same region of the image, we flag a conflict and say to the user that he or she needs to deal with this conflict in the image. And we did a prototype that helped us to play with the tool and analyze the timing that the tool needs to run. We run an experiment that showed us that running this kind of stuff in GPU decrease in at most 2 orders of magnitude the timing requirements for execution. Moreover, we got the Where is Waldo example in the beginning and compared the compression of that small change. It is also almost 2 orders of magnitude if I compare the delta with the full image that we changed. And after doing this image research, we start to think about videos. Video is actually a sequence of images. So if I'm able to run some diff, patch, and merge over image, it seems to be possible to do something similar with videos. And what we actually did was to get each one of the frames of the video and hash the frames with SHA1 algorithm. So we get the sequence of the hashes that represent the video. After that, we use LCS to align both videos and detect what is similar in both videos. When I get what's similar, it becomes easy to identify what has been changed in each one of the videos. We also do that using GPU, and we have the same properties that we had for the delta regarding image, we also have in video. So talking about diff, if I have 2 videos, in this case I put a space here only to ease the visualization, but the frames are A, B, C, D, E, and F, and the same here. When I run the alignment, I get A, B, D, and F as similar frames. It's the maximum sequence of similar frames that I get from the videos. And after align, it's easy to identify that these frames are the addition, if they are revision, or that these frames belong to video 2 if they are variants. I can identify that this frame is removal, and for these 2 frames, I know that they were changed. And what we do is to apply our diff for images over these frames and identify the diff that actually occurred in this segment of the video. The delta is basically applying back the operation. So if I have the additions, deletions, and deltas, I can apply back in the correct position and reconstruct the video. And the merge, we use the same algorithm that diff3 uses for text file, but we are using for videos. We run an LCS aligning the base version with video 1, and then we align the base version with video 2 and detect that the alignments that cross both video 1 and video 2. So we propagate these alignments to the merge, so we can have the parts that didn't change, and then for each segment between the parts that didn't change, we detect which video that changed that part. For example, here I have an addition, here I have a deletion, so I propagate the deletion, and here I have an addition, and I propagate the addition to the merged version. If I have changes in both parts, it means a conflict. So I can report that there is a conflict in this segment of the video. And here I have a prototype. That shows how this works. I'm first in selecting the video 1. I'm running only the diff algorithm here. So I select the video 1. After that, I select the video 2, two videos that I want to compare. And this is in Portuguese, sorry. But when he clicks here, I compare both videos. You note that it runs fast because it's running in GPU. It already did the diff. And when I move here, I can see that when I have similar frames, there is no delta. When I have different frames, I have a delta that represents the difference. Now they are similar, so I have no delta here. I put a subtitle in the second video, and only the subtitle is detected because I diff both videos. Here is the same again. Here I deleted the second video and I propagate the first video to the delta. And finally, I put some credits in the second video and it propagates the addition to the delta. And yes?
Okay, I'm a little confused about the algorithms for videos because every single modern video codec makes very heavy use of deltas, but you seem to assume that each and every single frame is complete and separable.
Yeah, that question is great. The first version that we didn't compress the video, and we got a very raw video that's far from reality, but allow us to run this experiment and check that hashing work because I can match hashes. What we are doing now, the question has to do, I assume that has to do with compressions because different video formats compress the image and I cannot get the same image if I change the video. They propagate the compression somehow. What we are doing now is to look for similarity hash algorithms. There are some of them. There are hash algorithms that I can subtract the hashes. It's different from cryptographic hash algorithms.
Right.
The cryptographic hash algorithms, if I have a small, tiny change, it goes to very different hashes on purpose. The similarity hash, if I have a very teeny change, they try to have a similar hash. They try to find a hash that's comparable to the other one. So what we are trying to do now is to use this kind of similarity hash algorithms and then subtract both hash and have a threshold. So if the frames are near, I will assume that they are the same. And I will not bother by the noise that I get from the frames. If they are above the threshold, so I assume they are different. We are working on that at that moment.
Yeah, but you're still throwing away all, I mean, the codec went to all the trouble of constructing very fine-grained deltas for you. That's what the codec is supposed to do. And you're basically throwing all of that away.
Yeah, you mean the base frame and all the deltas?
You've got the primary frame and then a series of deltas for.
What we are doing now is to decode the video.
But you're backing. You're throwing away all of those useful deltas. I mean, those deltas got constructed by way of, say, MPEG-4. Okay, a fairly exhaustive analysis, a block analysis of the fine-grained deltas from one frame to another, and you're just chucking all that out the window.
Yeah, I'm not sure how to deal with them. Probably it's possible, but it's not out of the box because these deltas belong to this base frame that's probably different from the base frame of the other video that I'm comparing because I add frames and remove frames. So it's interesting.
But you could. All right, never mind.
I will try to explore that, but I think it's not that easy to match the
I'm not saying it is.
Yeah.
Okay. I'm not claiming it is.
Thank you.
Come on now.
So
It's really hard, Rob.
yeah, the third part that we are trying to give as an example that Git or Subversion or another kind of system like this do not help us is when the system change at runtime. We are used to systems that we deploy, and after we deploy, the code do not change. And if someone finds a bug or has a new requirement, they file an issue, and we work on the source code, and we redeploy the system. But the system is still the same during the interval from one deploy to the other. And now we have some self-adaptive systems. These systems can censor the environment that they are inserted, analyze the context, see that changes occur in the context, use some reasoning, some model, some knowledge that they have about the components that they have, and change their configuration. So in these systems, we have an architecture configuration that is changing over time. How can we deal with this kind of system? So we used OSGI as an example of architecture that support this kind of component evolution at runtime, but we could do this over other infrastructure. And the idea here is to capture the architectural configurations of the system and try to figure out how the system evolves like we do for static evolution, but for dynamic and adaptive system. So here we capture the architectural configuration, we capture the context changes, so we monitor the context and know that something occurred in the context, and if possible, we capture the reason of change. The goals here is to provide some support for monitoring and for auditing the systems, because if they are self-adaptive and something goes wrong, I would like to know what happened. Is there a context variable that I couldn't imagine that go to a high value and it occurred or not? Is some failure in the model and so on? So what we do here is a self-adaptive system. We instrument some parts of the system to collect the reasons that the self-adaptive system analyzes during the change, the runtime context, the value of the context attributes, and the architecture configuration itself. After collecting this information, we provide some visualizations to try to figure out how the system evolved during runtime. So here I have the history view. This history view is basically a graph where each node represents architectural configuration. So the system starts with some configuration in revision 1. Something changed in the context, and it changes some components. I do not know which components, because here I'm in a high level. And I know that revision 2 is different from revision 1. Another change occurred. I went to revision 3. But here I had a third change that brought me back to revision 1. So I went back to the first architectural configuration that I had. And then I go to revision 4 and 5. Here I have other visualizations. For example, I have an architecture configuration visualization. I selected the revision 1, which is the first one that the system started, and I can see all the bundles, the OSGI bundles or components that were deployed at that moment, and the version of the bundle and the dependence among the bundle, the services that are provided and consumed by the bundles. We also have an architectural configuration, a context diff. The context diff, I select 2 revisions, and it shows me for each context attribute what happened from one revision to the other. In this example, I have some new attributes, I have some removed attributes, and I have some changed attributes in the temperature, for instance. We also have architecture configuration diff. When I select 2 revisions of the architecture configuration, and it shows me here, I know that there are revisions, so the color have meaning. It shows me that some components were added, some components were removed, and some components have their version changed. So I replaced some components in the system. If we can instrument the self-adaptive system to collect the reason that motivate the change, we capture in the issue represents what happened, what's the rule that triggered changes in the architecture. So we get the rule here, we have the actions that the self-adaptive system did, like it removed the window component and added the fan component. And this action propagate to the change, to the replacement of a version of another component. So I have dependence among components. So some small actions in a component may propagate to actions in other components. And here we have a view that tries to integrate all the previous views. It's a kind of an animation. I have the architectural diff here, I have the context diff here, and I have the issue here. So we can navigate through the versions and see what happened from one version to the other. Actually here, we are navigating the first graph that I showed, the history graph, and we are putting together all the visualizations that we have about the components evolution. So the idea of these presentations is to show you that we have much more things to do regarding version than we already have done. So we have a great infrastructure for version. I assume that most of you or all of you use Git or Subversion on a daily basis, but we still have some challenges to do in this version area. There are some other stuff that I'm doing in Brazil. If you are interested, we can talk about it, and we can manage to discuss this subject. We are working with semantic conflicts detection in UML. What I talked to you has to do with syntax. Like I select the class as an atomic type. If two people change the same class, I detect a conflict. But what about semantics? What happens if two people change the model in a way that there is no conflict in the structure of the model, but they are doing things that do not work well together? The meaning of the things. We are doing the same regarding semi-structured data. What happens if two people work at the same time over an XML file and they want to combine the XML file? Do they did things that conflict in the semantic way or not? Another work that we are doing in Brazil has to do with merge optimization. We have a classic merge algorithm that receives two versions that should be merged and a base version that is used to extract the operations that two people did in parallel. But now we have, when we think about Git, two branches. When you clone to your machine, you do lots of intermediate commits in your machine. And the other people did the same. So we can use these small steps that you did in your branch and the small steps that the other person did in his branch to combine in different sequence, run some optimization algorithm, and detect the best way to merge to combine the changes. We are also working with topology identification. If you are using to Git, it's a distributed version control system. You can use it having GitHub as a central repository, but you can also use it with peers. Like you send some code to a colleague and he sends some code to other person. We have a problem because it's hard to figure out what is the topology of the development. I do not know how many people are working, how many people have which commits and so on. So we have a work in trying to figure out how is the topology of the repositories in a distributed version control system. And finally, we have some work on provenance. Provenance has to do with data evolution. It can be seen as a version of the data at runtime. So it's usually used to detect cause effect among data. I run a program, I receive a result, and I'd like to know what did I do that improved this result. So I can go to the source code and analyze the commits that I did. I can go to the execution traces and see the dependence that this data has on other files that exist in the file system, and so on. We are trying to use this for games. After you have a game section and you're happy because you won, I would like to provide some feedback of which actions did you do that helped you to win the game. And we are also doing this for Python scripts, which are being used by scientists to write scientific experiments, and they want to answer why they get some good or bad results. So going back to the presentation, my main message is that we now currently have lots of version control system. It's nice, and now people use them on a daily basis. However, they have almost no theoretical foundation. Each version control system is a bunch of codes that do not follow a specific theory. If we look at the diff tree, which is used as a base diff and merge algorithm for most of them, they have lots of unanticipated behavior. So the feeling that I have is that we are patching a broken solution. I don't know if you know the history of Git, but Linus said once that Subversion is a pointless project because it basically fixes CVS. But thinking the same way, Git basically fixes some problems in Subversion. We steal over a file system models. We cannot version objects. We cannot version things that are not text-based files. Or at least we cannot version in a good way. So the road ahead, it's hard to say, but if we look to the side, we see the relational database community. These guys could create a very strong theoretical foundation over the relational model. Now we have lots of relational databases that are holding important systems on a daily basis. And they have a unified query language that allow us to deal with different databases, replace the different databases, and so on. So my feeling is that we need a stronger foundation for versioning. I'm not sure if the metaphor of file system still holds for versioning, as we are having lots of different types of artifacts besides source code. And I cannot answer that, but I would like to have, in the next years, a data model that accommodates source code as well as any other type of artifact that we may conceive to developer software. So I'd like to thank some students and colleagues that work together with me in these three subjects. And here is the short bibliography. Open to questions.
Regarding the self-adapting systems,
Yes.
you said that you need to instrument the code. So I assume there's some infrastructure or monitoring system running also along with the monitor system. So my question is, do you need to couple your software to the infrastructure to?
Yeah. What did we do? Actually, we got the idea, the subject, and in our university, there are some people that are developing a system for home care for elderly people that has lots of sensors and monitor the house, and they need to adapt the situation depending on some measures that they get from the people, from the environment, and so on. So what we did was to instrument this project to have a kind of a validation of the idea, but there is a part of it that is quite independent from the system. The collection of the context attribute, it comes from the sensors. So I need somehow to instrument the sensor and get the values, or instrument the databases that the sensor stores the data. The collection of the issues is the harder part, because I need, each self-adaptive system has a different mechanism to trigger changes. And we need to go to the rules that the system uses and capture the rules and map to the issue concept. The idea of the issue is to have a map to the concepts that we are using in configuration management, like issues, commits, and so on. But the last one, the architecture configuration itself, it's not coupled with the system, but the OSGI infrastructure. So we have bundles in the OSGI infrastructure. What we do, when we deploy ourselves in the OSGI infrastructure, we check all the other bundles that exist and mark them as application independent. That means that we do not want to monitor the bundles that exist before the deployment of the application. After we are there, our sensor is there, the application can be deployed in the OSGI container, and we receive notifications from the OSGI infrastructure that new components have been added. And we assume that these components are the application components. So the instrumentation of the architecture configuration is kind of general, but the other, we need to instrument the application itself.
Thanks.
Yes?
So, have you thought of different kinds of images, like 3D images, right? In which case, maybe the resulting rendered image is not so important as the model behind that is created pre-rendering.
Actually, one of the things that we would like to do, I don't know if here is different, but in Brazil, the PhD students go to the qualifier in the second year, and he has more 2 years to finish the PhD. Our plan with this PhD student that is working with images was to work with the meshes that represent the 3D model. So he wants to do diff direct in the model. And when we talked about that with the committee, they said, no, forget it, because you have lots of problems with image and video to deal with. So we are not doing that, but something that we are planning to do, now it's quite simple, because we get 2 images and we assume that they are aligned, and we go pixel by pixel to detect the change. More than that, it's completely syntactic. We do not have the semantics of the image. Something that we are planning to do now is try to detect the objects that belong to the image, and try to do a diff in the level of the objects that we could detect in the image. And we already have some algorithms available in the literature that are able to detect objects even if they are in different angles and so on. So it would provide us with a kind of semantic diff of image. I could have an output like you deleted some elements and you put some other elements. So this is the way we probably follow for images. Yes?
Yeah, I want to spin off from that question. I was thinking about operations that applies to all the pixels. Maybe if you change the bright or canvas size or gamma, whatever. There are small changes, but will increase the storage required a lot. So is there any, I don't know, have you thought about maybe storing the computation behind instead of the result?
Yeah, you're talking about operation-based.
Yeah.
I talk all the time about state-based versioning, but there is another way of dealing with version that's storing the operations. It's okay if you have access to the environment that the user is interacting. But if I have access only to the result of the interaction, sometimes it's pretty hard to identify which operation the user did. Yes, you're right. Depending on the operation, we call it global operations. If you do a global operation in the image, the diff will reflect the global operation. Depending on the operation, the diff will be a plain image in a certain color, which is good because it compresses a lot. But there are some other operations that the diff becomes something very strange and it cannot compress. What we did to attenuate this problem, we compare the size of the diff with the size of the next image. If it's near, it's not too different, we store the next image. So if you look at the repository, you have an image, lots of diff. It resembles what the video does. An image, lots of diff, and then an image, and lots of diff, and then an image. But it does the decision based on how big the diff is after a global, usually after a global operation.
Thanks. So,
Yes?
has there been any idea like to patch Git, for example? Like, are you planning to add any of these features to?
Yeah. What we ran some experiments, but we didn't talk to people that are working the Git repository. It's very easy to patch Git at the client side because it has extensive APIs that you can plug your own diff and merge algorithm. But in the server side, it would need to go inside the Git code and do some modification. The problem here is that we rely on GPU to running this operation fast. And if you get a MacBook Air, for instance, it has no GPU available for me. So it would be, I think, a nice engineering task to figure out a way to use the appropriate algorithm if you have computing power that allows you to use this algorithm. And if you are running in a machine that do not provides you GPU, you will stay with the whole versioning. Otherwise, you have very long commits because it takes some time to process the images and the video. But this is nice. I'm not sure if it's research, but it's something that would be useful for the people that are using it on the daily basis. But again, if we look at this slide, I still have this feeling. Because I'm trying to plug inside a system that has a broken data model, something to deal with this kind of I think if we put together lots of smart people, we can conceive something that's more general and more easy to embrace change.
Any one final question? Are we ready for snacks downstairs? All right. Thank you all for coming, and thanks everyone.
Thank you.